Hi, we'd like to factorise this polynomial p over the complex numbers, over the real numbers, and then look and see what extra information that can give us. So p is 1 plus z squared plus z cubed plus z to the fourth. And you may know that this is a factor of z to the fifth minus 1. So the first thing is we use that, we solve z to the fifth minus 1 and hence factorise p into linear factors over the complex numbers. Now I'm going to assume that you know how to solve z to the fifth equals 1. This is just the fifth roots of unity, so let's write them down. So the solutions of z to the fifth equals 1 are the fifth roots of unity, namely, we'll take e to the minus 4 pi I on 5, e to the minus 2 pi I on 5, e to the minus 0 pi I on 5, or e to the 0 pi I on 5, which is 1, which is obviously a root of unity, and e to the 2 pi I on 5, e to the 4 pi I on 5, okay? Now this means we can factorise z to the fifth minus 1 using these linear factors. Z to the fifth minus 1 is z minus 1, the product of all of these z minus a root. So we just write them all down. And I'm going to group them in this way because I know what's coming next. E to the minus 2 pi I on 5, z minus e to the 2 pi I on 5, okay? Now, that's the solution of z to the fifth minus 1, factorised over the complex numbers. We really want the factors of p. But z to the fifth minus 1 is just z minus 1 times p. So let's use that fact, which is a very useful fact. Of course, you can replace this 5 here by n and this 4 by n minus 1, sum all the way up, and this identity holds. So since we have this, we can clearly cancel the z minus 1 on both and obtain a factorisation for p. P of z, which is this second factor here, is the product of all the other factors other than the first one. So you just write that out again. And imagine these factors are just up here on the right. Okay, so we factored p into linear factors over the complex numbers, and now we move on to part B of the question. Find all linear and quadratic factors of p with real coefficients. We want to factor p over the reals. Okay, clearly we haven't done that yet. These coefficients that you would get, well, you can see a lot of complex numbers here that are not real. However, we've grouped them so that the roots, which are complex conjugates of each other, are together. So all we need to do to solve part B is to multiply these first two factors together and multiply the second two factors together. So let's see how that goes. Let's say from part A, we have P of Z is, well, what happens when you multiply these two? Z minus e to the minus 4 pi I on 5, Z minus e to the 4 pi I on 5, they're complex conjugates of each other. You'll get Z squared, then you get a minus the sum of these two roots. And we know the sum of these two roots is going to be 2 cos 4 pi on 5 from this. Let's write it down and get it right. That's the linear coefficient, And when you multiply these two roots together, that'll give you the constant coefficient of the product of these two, and that's just going to be 1. So that's our first quadratic coefficient, and this is a real number. So that's a real factor. And the same sort of thing happens, I'll put it underneath, for the next two. You do it again with these two, and you're going to get 2 times cos 2 pi on 5 as the linear coefficient. Okay? So now we factorise p, firstly over the complex numbers, and secondly over the reals. Now in part C, we are going to do a really nice trick. First we divide p of z equals 0 by z squared and make a change of variables x equals z plus 1 on z. And we're being asked to deduce that for any z such that p of z equals 0, we also have x squared plus x minus 1 equals 0. And that's going to help us to solve part D. So let's just do what they suggest. Okay? Dividing p of z equals 0 by z squared, what is it going to give? Well, we had 1 plus z up to z fourth equals 0. So the 1 is going to give you 1 on z squared. The z will give you 1 on z. The z squared term gives you just 1. The z to the cubed term will give you a z, and the z to the fourth term will give you a z squared. And this is 0. And now we make our substitution. X is z plus 1 on z. So we can easily see, I guess, this term and this term together are going to give us x. And looking at what we're aiming to get at, we can see an x squared is going to show up somewhere. So let's see what happens. What is x squared actually? X squared is z plus 1 on z all squared. So what you'll get from this is z squared that we can see here plus 1 on z squared that we can see here, but you'll also get the cross term, 2 times z times 1 on z, which is just 2. We don't have 2, we only have 1. So we can see that if we replace 1 on z squared plus z squared by x squared, we've introduced 1 more than what we've got, and that's why we're going to have to subtract 1. So let's just say, hence, we have, how shall I write this? 1 on z squared, well, this expression we got up here, 1 on z squared plus 1 on z plus 1 plus z squared is actually equal to x squared plus x that we identified, but we have to fix it by subtracting 1. And so if this left-hand side is equal to 0, then so is this right-hand side, let's say as required. That'll be enough to prove what we need to prove. Okay? Now in part D, we're going to put this together and prove 2 really nice facts. We're going to prove that the cos of 2 pi on 5 is this number, minus 1 plus root 5 on 4, and the cos of 4 pi on 5 equals minus 1 minus root 5 on 4. And how else would you prove these facts? Double angle formulas are not going to help you really. Okay, so let's see how this goes. Recall from part A that the roots of P, the solutions of P of z equals 0, are e to the minus 4 pi I on 5, e to the 4 pi I on 5, e to the minus 2 pi I on 5, and e to the 2 pi I on 5. All the fifth roots of unity that are not equal to 1. And we've got them in complex conjugate pairs. Now remember that substitution, x equals z plus 1 on z. When you take z to be any of these, 1 on z is just going to be its complex conjugate. So if I choose z to be either this one or this one, what's x going to equal? If z is, let's say, e to the 4 pi I on 5, then you can check that x is the sum of these two, which is twice cos 4 pi on 5. okay, twice the real part. And similarly, if z is e to the 2 pi I on 5, then x is just twice the cosine of 2 pi on 5. All right? And we said in part C that whenever p of z is 0, then the x that we get here is a root of x squared plus x minus 1. So hence, these values, these numbers, are roots of x squared plus x minus 1. But what are the roots of this quadratic? Well, we can just solve them using the quadratic formula. And when you do that, you'll find that you get minus 1 plus or minus root 5 on 2. Okay? So we've shown that these two numbers together make up these two roots. One of them must equal minus 1 plus root 5 on 2, and one of them must equal minus 1 minus root 5 on 2. And obviously, once we've sorted out which way around they go, we can just divide by 2 in each case, and we will have answered the question. Okay? So how do we know whether 2 cos 4 pi on 5 is minus 1 plus root 5 on 2 or minus 1 minus root 5 on 2? Well, we can look at where the angles 2 pi on 5 and 4 pi on 5 fall on this, well, the Argand diagram, I guess. And you can, I've put these little dots in to help me to try and make my diagram neat, but you can see that this first one up here, this is e to the 2 pi I on 5. So this angle here is 2 pi on 5. Okay? And the other one, all the way over here, pretend that's a straight line, please, is e to the 4 pi I on 5. Now what you notice is the this is the real axis. The real part of e to the 2 pi I on 5 is positive. The real part of e to the minus 4 pi I on 5 is negative. So the positive root that we have here must equal 2 cos 2 pi on 5. So looking at sines, let's say, tells us that 2 cos 2 pi on 5, the positive one, must equal minus 1 plus root 5 over 2, because obviously root 5 is bigger than 1, and it's easy then to conclude that the cosine of 2 pi on 5 is what we were told. Okay? And the other way around. 2 cos 4 pi on 5, the negative one, must be minus 1 minus root 5 on 2. And then you divide by 2. And that completes the proof of this example. One other thing I might tell you, when I was trying to figure out where these numbers were, I thought of a little trick. I'm not sure if I'm going to be able to do this neatly. You could draw a star, a 5-pointed star, and it would be something like that to give you a rough idea where these complex numbers fall on the Argand diagram. Thank you.